Good morning, students. Myself, Dr. S. Devikala, Associate Professor in the Department of Chemistry, SRM Institute of Science and Technology. In today's class, we will see about X-ray diffraction. What is X-ray diffraction? How a X-ray diffractometer works out, and what are the applications involved. Let us see one by one. So, as we all know, there are three phases of matter, that is gas, liquid, and solid. In case of solid molecules, the molecules are said to be rigid. In case of liquid molecules, they are loosely packed, whereas in case of gaseous molecule, they are more loosely packed. So here it is rigid, loosely packed, whereas here it is more loosely packed. We know that. So what is a solid? So solid, we know very well. It has definite shape, definite volume, highly incompressible, rigid. It constitutes particles, that is, ions or molecules, held closely by strong intermolecular forces. So solids generally have fixed position of constituents. We know that there are two types of solids. One is crystalline, the other one is amorphous. So let us see what are crystalline solids. In case of crystalline solids, the building constituents arrange themselves in regular manner throughout the entire three-dimensional network, that is long-range order. So existence of crystalline lattice. A crystalline lattice is a solid figure which has a definite geometrical shape with flat faces and sharp edges. You can see to the right side some of the crystals of various minerals has been given over here. Down you have the diamond crystal. Incompressible orderly arranged units. They have definite sharp melting point, anisotropy in nature, definite geometry, diffract X-ray beams, that is crystalline solids, it will diffract X-ray beams. For example, NaCl, CaCl, diamond, etc. Let us move on to amorphous solids. The word amorphous, that is derived from the Greek word amorphi, meaning shapeless. Crystalline means they have definite shape, whereas amorphous means shapeless, without any shape. So no regular but apposite arrangement of atoms or molecules, that is absence of any long range order. Also considered as non-crystalline solids or supercooled liquids. So what is the other name for amorphous solid means non-crystalline. They are highly non-crystalline in nature, or we can call it as supercooled liquids. No sharp melting points. In case of crystalline, they are anisotropy, whereas in case of amorphous solid, they are isotropic in nature. No definite geometrical shape. They do not give X-ray diffraction, that is very weak. Some of the amorphous solids are glass, rubber, and plastics. So if you look at this X-ray diffraction pattern, if the solid is highly crystalline, you will get a sharp peak like this, whereas amorphous broad. So with the help of X-ray diffraction pattern, one can easily distinguish which is amorphous and which is crystalline. Then let us see about the different types of crystals: ionic crystals, covalent crystals, molecular crystals, and metallic crystals. In case of ionic crystals, they have positive and negative ions, highly hard and brittle, strong electrostatic forces. Since strong electrostatic forces they have, it's very difficult to melt them, so high melting point. Example, sodium chloride, cesium chloride, and so on. The second category, covalent crystals. Covalent crystals constituted by neutral atoms which are held together by covalent bonds, hot solids. As a result, high melting point, poor conductor of electricity. Example, diamond. Then the third one, molecular crystals constituted by neutral molecules held together by weak intermolecular interaction. Whenever if we say weak intermolecular interaction, it is nothing but van der Waals forces. Apart from that, hydrogen bonding. Soft solids have low melting point. Example, sugar. Metallic crystals, these ions by a sea of mobile electron. Soft to very hot, high tensile strength, good conductor of electricity, high density. Since the name itself metallic crystal, example will be any metal. Let us see what is crystal lattice and unit cell. So in this slide, you can see the arrangement of Na plus and Cl minus ions in sodium chloride. We know very well, even in the solid state, each Na plus is surrounded by 8 uh, Cl minus ions and vice versa. So a lattice is a regular infinite arrangement of points in which every point has the same environment as any other point. Since lattices consist of indefinitely repeating patterns, one need only to look at the smallest repeat unit to describe the lattice. So unit cell, it is nothing but it is the smallest repeating unit. Crystal lattice and unit cell, a regular three-dimensional arrangement of points in space is called crystal lattice. I'll repeat, a regular three-dimensional arrangement of points in space is termed as crystal lattice. Unit cell is the smallest portion of the crystal lattice. When repeated in different direction, it generates the entire lattice. So in order to construct a house, the fundamental unit is bricks. So bricks are the unit cell. Okay, if we keep on arrange the bricks, finally we'll end up with a house. So unit cell is set to crystal like a brick to a house. So left side you can see the representation of space lattice and unit cell. On the right side, representation of dimension of a simple unit cell. So this is the fundamental building block. A unit cell is characterized by a dimension along three edges A, B and C and the three angles between them. So the angles are mentioned here, alpha, beta and gamma. The edges may or may not be mutually perpendicular. Where A alpha is the angle between B and C, beta is the angle between A and C, and gamma is the angle between A and B. I'll repeat, where A alpha is the angle between B and C. So where is B? You have B and C. Alpha you can find over here. So alpha is the angle between B and C. Similarly, beta is the angle between A and C. Gamma is the angle between A and B. So a unit cell is nothing but it is the fundamental unit. So in this slide, you can see 7 crystal systems, namely cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, and triclinic. Along with that, the essential symmetries, also the allowed lattices given over here. You can see the shapes of different crystal systems: cubic, tetragonal, orthorhombic, monoclinic, triclinic, trigonal, and hexagonal. Next one, crystal planes. With the help of crystal planes, we are going to derive the Miller indices. Let us see what are Miller indices also. So a lattice plane is a plane which passes through any 3 points which are not in a straight line. So a set of parallel lattice plane is characterized by its Miller indices denoted as HKL. HKL, it is nothing but Miller indices. The set of lattice plane HKL divides A into H parts, B into K parts and C into L parts, where A, B and C are the length of unit cells along X, Y and Z axis respectively. So in this diagram you can see X, Y, Z. These three are the coordinate axis with its Miller indices value HKL. So the following treatment of the procedure used to assign the Miller indices is a simplified one considering a cubic crystal system. So first step, in order to arrive at the Miller indices, we need to identify the intercepts on the X, Y and Z axis. So in this case, the intercept on the X axis is at X is equal to A, but the surface is parallel to the Y and Z axis. Therefore, there is no intercept on these two axes. In fact, the intercept to be at infinity for the case where the plane is parallel to an axis. The intercepts on the X and Y axes are therefore A infinity, comma infinity. The step 2 will be we have to specify the intercepts in fractional coordinates. So coordinates are converted to fractional coordinates by dividing the respective cell dimension. For example, a point x, y, z in a unit cell of dimension. So a into b into c has fractional coordinates. So x by a, y by b, z by c. So in case of cubic unit cell, each coordinate will simply be divided by the cubic cell constant, that is a. So this gives the fractional intercepts as a by a, infinity by a, infinity by a. If you simplify this, the answer is 1, comma, infinity, comma, infinity. Then the step 3, take the reciprocal of the fractional intercept, which will give the Miller indices. So the final manipulation generates the Miller indices, which by convention should then be specified without being separated by any commas or other symbol. When we write Miller indices, we have to write like this only, 1, 0, 0. There should not be any comma or space in between. That is what given over here. The Miller indices are also enclosed within standard brackets when one is specifying a unique surface such that being considered here. The reciprocal of 1 and infinity are 1 and 0 respectively. Therefore, the Miller indices for the above plane, it will be 1, 0, 0. So likewise, we have to determine the Miller indices for the green and yellow planes. That is worked out here. You can go through this. You can have a glance. So for the above yellow and green planes, the Miller indices will be 0 and 0 and 0, 0 n. So one more example for your understanding with answers. Some more for to work out. Then let us see about the wave interferences. You have two types of interference. One is constructive, the other one is destructive. If I say constructive, what does that mean? Two waves are in phase, whereas destructive, two waves are in opposite phase. Same phase, then it is constructive. Opposite means it is destructive. We know this. Let us move on to the Bragg's law of diffraction. So when the rays incident on the crystal, it gets diffracted. So here the first ray, it is given in terms of green line. So the incident ray as well as the scattered wave, whereas the second ray. So from this also we can very well calculate the HKL lattice plane values given over here. So the extra path traveled by the second ray is equal to AO plus BO. Where is AO? Here. You have AO plus BO is equal to d sin theta plus d sin theta. So that gives you 2d sin theta. So in order to create constructive interference, two rays must be in phase. Just now we have seen this point. That means the extra path traveled by the second ray must be equal to integral multiple of the wavelength, that is lambda. Therefore, the equation becomes 2d sin theta is equal to n lambda. This equation only it is called as Bragg's law, well-known equation, where n is order of reflection, wavelength. Lambda is nothing but a wavelength. D interplanar spacing. So this is the typical X-ray diffractometer, the actual diagram, how the instrument will look like. Thank you.